Welcome to this video on periodic trends. And today we're going to use the periodic table to describe how several characteristics of elements vary as we move from left to right across a period, but also as we move from top to bottom down a group. And those three characteristics which we're going to examine are going to be atomic radius, ionization energy, and electron affinity. So don't worry if you don't know what those terms mean just quite yet. We're going to define them as we go. So the first characteristic we're going to look at is atomic radius. And so normally when we think of radius, we tend to think of the distance between the center of a circle, or maybe the center of a sphere, and its outermost edge. But it's kind of tricky with atoms, because even though we tend to think of them in sort of in our minds or on paper as spheres, they're not perfect spheres, because this outer edge is made up of electrons, which are constantly moving, and so technically the radius keeps shifting. But the way we define atomic radius is we take an atom bound to itself, so say hydrogen gas in this case. We can measure the distance between the two nuclei, and we say that this distance, r over 2, we divide it by 2, is equal roughly to the atomic radius, and that's close enough for our purposes. So right now we're going to take a look at what happens when we move left to right across a period. So maybe let's pick a specific period of the periodic table to examine. How about we choose this one, period 4, starting with potassium and ending with krypton. So we move from left to right, two things are going to happen. Firstly, of course, we're going to increase the number of protons in our nucleus, as well as neutrons, but we're really interested in the protons. And so we're going to have increased nuclear charge. I've written that right here. And the result of that is we're going to have increased attraction. Increased attraction on our outermost electrons, because more positive charge is going to exert a greater force on those electrons, a greater electrostatic force. We're also going to add electrons, because remember, as we add every proton, these are elemental atoms. They have the same number of electrons as they have protons, so as we add protons, we're also adding electrons. And this is going to increase repulsion on the outermost electrons of our atom, because electrons all have negative charges, and so they repel each other, and they're therefore going to decrease their attraction to the nucleus. But let's also think about how we're adding these electrons. Because this is the same period, I think this is period 4, we're adding electrons to the same quantum number. They're all going to be in period 4, in a 4s orbital, a 4p orbital, or a 3d orbital, which we can say a 3d orbital is pretty close to a quantum number of 4. And when we add electrons to the same quantum number, we don't greatly increase repulsion. Let me write that for you. It's an important concept. Electrons added to same quantum number, so in this case the 4th period, same quantum number, do not greatly increase repulsion. Don't greatly increase repulsion. And so even though we've got these counteracting forces, this increased attraction because of the nuclear charge, increased repulsion because of more electrons, the increased attraction, maybe we can say the delta attraction, is greater than the delta in repulsion. What this means is as we move left to right across a period, we're going to see atomic radius decrease. We're going to see atomic radius decrease, because there's going to be a greater pull on the electrons from the nucleus, from the more positively charged nucleus, and there's going to be greater repulsion from those electrons. And we can illustrate that in the following way. So we've got lithium, which is in period 2, and fluorine, which is also in period 2. So as we move from left to right, fluorine's going to have a lot more protons than lithium. It's also going to have more electrons. So in lithium, the electrons are going to be 3 electrons. They're going to be hanging out like this. And let's see, there are going to be 9 electrons in fluorine. And so we can say the electrons in fluorine are actually going to be much, much, much closer to the nucleus than they are, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, than they are in lithium, because of all this positive charge over here. And because they're all added to the same quantum number, we're not adding them to shells that are a lot farther away from the nucleus. We're adding electrons to shells which are all on the same level, and so the electrons are going to be pulled in closer. So if we look at the average radius in this fluorine atom, as compared to the radius in this lithium atom, the radius in fluorine, which is on the right side of the period, is going to be much smaller than on the left-hand side. So as we move left to right across a period, atomic radius decreases. 1, because of increased nuclear charge, and 2, because we're adding electrons to the same quantum number. What about moving down a group? When we move down a group, again, 2 things happen. We have more increased nuclear charge. We certainly have increased nuclear charge, more protons, increased nuclear charge. We also have electrons added to higher quantum numbers. Electrons added to higher quantum numbers, to higher, we can say maybe energy levels. Energy levels. Let's look at a practical example. So let's say we take the alkali metals. As we move from lithium to sodium, we add protons. We go from 3 protons to 11 protons. We also add electrons, not to the principal quantum number 2 orbitals, we add them to the 3s orbitals. And because we do that, the electrons are going to be significantly farther away from the nucleus than they would be if they were added to the same orbital. We can illustrate that similarly by looking at lithium and sodium. And so with lithium, we've got 3 electrons, and so they're going to be similar to the last diagram we drew, hanging out like that. With sodium, we've got a bunch of core electrons, just like lithium does, over here, over here, over here, but we're also adding electrons to the 3s level, as opposed to the 2s level in lithium. And that 1 electron in the 3s level is going to be significantly farther away than the 2s, so it's a higher energy level. What's also going to happen is these inner electrons, they're actually going to do something really interesting. They're going to shield that outer electron from the increased nuclear charge. This phenomenon is known as shielding. And so because those electrons are negatively charged, they're going to exert a repulsive force on that electron, which is going to cancel out roughly the increased attractive force which resulted from adding adding protons to the nucleus as we move down a period. So in this case, repulsion is going to be greater than increased attraction. Our delta repulsion is going to be greater than our change in attraction. So we can say that as we move down a period, down a group, we can only move left to right across a period, down a group, atomic radius is going to increase. Because although we have increased nuclear charge, electrons are added to higher energy levels, to higher quantum numbers, and electron shielding negates the increased nuclear charge. Moving on to ionization energy. Ionization energy is defined as the energy required to remove an electron from an atom. And we describe ionization energies in terms of things like first ionization energies, second ionization energies. And the second ionization energy, as the name might imply, is the energy required to remove the second electron from an atom, etc., etc. And so in general, the second ionization energy is larger than the first, because it takes more energy to remove the second electron than it takes to remove the first. But right now we're interested in looking at the periodic trend in ionization energy. So from moving not right to left, rather from left to right, we all make mistakes, and down a group. So first let's look at left to right. Well, for pretty much the same reason as we described up here in terms of atomic radius, moving left to right, we've got increased nuclear charge, more electrons, but the attraction wins out. We said that there's greater attraction to electrons as we move from left to right. So there's attraction to electrons increases as we move left to right across a period. Since atoms on the right-hand side of the periodic table generally attract electrons with more energy, with more force than they do on the left-hand side, it's going to take more energy to strip, say, if we look at a specific period, it's going to take more energy to remove an electron from oxygen than it is going to take to remove an electron from lithium, because oxygen holds on to its electrons much smaller and much harder because it has a smaller atomic radius. So we can say that for ionization energy, as we move left to right across a period, ionization energy is going to increase. So it's directly inversely proportional to atomic radius. The same thing is going to hold true when we move down a group. When we move down a group, we describe this in terms of atomic radius, increased nuclear charge, but because we're adding electrons to higher energy levels and shielding goes on, the atomic radius is going to increase and the electrons are going to be bound less tightly to the nucleus. Because electrons are bound less tightly to the nucleus, their attraction to the nucleus is going to decrease. So attraction decreases. Because attraction decreases and there's less force pulling on that electron from the nucleus, ionization energy, the energy required to remove an electron, is going to decrease. So ionization energy decreases as we move down a group. And so, again, if we look at a specific group in the periodic table, the ionization energy of lithium is going to be much higher than the ionization energy of cesium, because lithium holds on to its one valence electron much harder than cesium does. And that is the periodic trend in ionization energy. Before we move on to electron affinity, I just want to make a quick note about ionization energy. We said that the first ionization energy of any element is always higher than the second. But a question that comes up a lot on the SAT and on the AP is they give you a graph of ionization energies and they'll say explain why there's this jump right here. And so if we have potassium, this is the graph of ionization energy for potassium, we're going to see that potassium has one valence electron. We're going to see that potassium has one valence electron. And that valence electron is represented by this ionization energy, the first ionization energy. And so we can see that the first ionization energy is much smaller than the second. So as we move up this graph, ionization energy increases. So ionization energy increases. The second is much higher than the first, and we can explain that by saying that this electron is in the fourth, has a quantum number of 4, and this is a valence electron, but these electrons are core electrons. These electrons are core electrons. They're not valence, and they occupy a quantum number of n equals 3. So they're much closer to the nucleus, they're much more tightly bound to the nucleus, and therefore it takes much more energy to remove them from the atom. So the second ionization energy is much higher than the first. And the same thing happens in this jump here. Because these electrons are from an even lower energy level, these are from n equals 2, they're even closer to the nucleus and therefore it requires even more energy to remove them via the ionization energy. So that's just a little question. So whenever you're asked why there's a big jump between two ionization energies, it's usually because we're moving from valence electrons to inner core electrons. Our final periodic trend is going to relate to electron affinity. And electron affinity we just define as the energy change following the addition of electron. It's kind of the inverse of ionization energy. How much energy is given off, or how much energy do we need to add an electron to an atom? And generally when we say an atom has a large electron affinity, we say that it gives off a lot of energy when we add that electron. So electrons or atoms which really want an electron, which maybe need an electron to complete their octet of 8 electrons, will give off energy, will have a large electron affinity, whereas when we have to add energy to an atom, to add an electron, so when an atom really doesn't want to add an electron, we say that that atom has a small electron affinity. And generally, metals want to give up an electron, so they're going to have low electron affinities because they don't want to gain electrons, whereas nonmetals want to gain an electron. They want to gain electrons to complete their octet because they'll be closer to 8 when they gain an electron. And so briefly, I don't want to waste your time here, this video is getting a little bit long. We can just briefly summarize what's going to happen when we move from left to right across a period and we move down a group. Again, we've said this multiple times, when we move left to right across a period, we're going to have increased attraction. Increased attraction. Because it's increased attraction, atoms are going to be more stable when we add electrons. Again, because these atoms have 5 electrons, 6 electrons, 7 electrons, and so they'll only need a few to reach 8, so they're going to want to gain those electrons to reach 8. And so therefore we see an increase in electron affinity, so atoms give up more energy when we add electrons, except for the noble gases. So the noble gases are the final period, or rather the final group of the periodic table, and so electron affinity is going to increase as we move left, right, until we reach the noble gases. And the noble gases really aren't going to want to get to receive an electron because they've got a complete octet, and receiving an electron is going to make them much more unstable. So we generally see increased electron affinity except with the noble gases. What about moving down a group? Well, we know when we move down a group, we've got decreased attraction. Decreased attraction. So really, we should see higher electron affinities because it shouldn't take. Let's see. How do I explain this? As we move down a group, there's going to be decreased attraction, and so there's going to be a smaller energy change when we add electrons because there's not going to be as great a force acting on the nucleus. So for metals, we're not going to need to add that much energy to add an electron because that electron isn't going to be tightly bound. Similarly, for nonmetals, it's going to be more tightly bound than it would be for metals, but it's not going to be as tightly bound when it's down at the bottom of a group than it is at the top of a group. The reason it's so hard to explain what happens to electron affinity as we move down a group is there's really no noticeable pattern. The changes are so small and there are so many exceptions that we really don't describe a pattern as we move down a group with electron affinity. Just to summarize, we've taken a look at atomic radius and said that it decreases as we move left to right across a period and increases as we move down a group. We've said ionization energy is the inverse of atomic radius in that it increases as we move left to right across a period and decreases as we move down a group. And electron affinity, we said, increases as we move left to right across a period except for the noble gases, and there's no real pattern as we move down a group. And the main thing to remember when you're trying to explain periodic trends is to think about where you have increased attraction and whether you're adding electrons to the same quantum number or a higher quantum number. And when you're adding electrons to a higher quantum number, you have to take into account electron shielding, which generally negates the fact that you have increased nuclear charge. Thank you very much, and I'll see you in the next presentation.